Okay, perfect. So, okay, I ask to keep the talk about 22 minutes to allow time for questions, and I may turn on my camera to give you a sign when 20 minutes are passed. So I don't see here our third speaker. I hope that he is going to join us later, but yeah, without further ado, you can start. Our first speaker is Ben Solo from the University of St. Andrew, and his talk is about Bayesian causal inference for environmental exposures using potential outcomes, challenges, and opportunities. To you, Ben.
Thank you very much, Monica, and thanks very much for inviting me to this. So when I first agreed to give a talk, I still had some very preliminary work in this area, so I wasn't sure exactly what I was going to have ready for this talk. So as it turns out, the talk's going to be a little bit more specific than what I planned to be, and but still very much on the same area. So this is particularly about Bayesian causal inference in the case where we have zero inflated continuous data, but again, using the idea of a potential outcome framework. So just to start off with some acknowledgements, this has been collaborative work with Maribel Bind at the Massachusetts General Hospital in Boston, and Young Lee, who was one of Maribel's former postdocs at Harvard, but now works in industry. And the zero inflated part of the talk will be in collaboration, or has been in collaboration, with two research associates at the University of Glasgow. So I'm sure many of you know this already, but just to give a brief background, the causal inference framework allows us to study causal mechanisms between experimental inputs and outputs, which goes above and beyond purely correlative studies, which are often quite common in canonical inference. And the problems are particularly in the case where we have observational studies. Generally with causal inference, we would rather have randomized controlled trials as the kind of gold standard. But in many cases, such as particularly in things like environmental exposure, we don't actually have the ability to control the environmental environment around us. We just are passive observers, and then trying to do some sort of trial emulation or an approximation to a trial setup has to then be done post data collection or independent of the data collection. So that's really where we're coming from here, is from an observational study perspective. Now, the approach we're going to take was originally developed back in the 70s by Rubin and falls under the Bayesian causal inference framework. And it really stems from the idea that ideally, in order to be able to develop causal mechanisms, we would ideally want to measure the outcome of an experiment, whatever that experiment may be, where we apply both a treatment and a control setting to all of the individual experimental units, or at least some sort of randomized trial where people or individuals with a similar background or similar underlying properties are exposed to both the control and the treatment effect. And therefore we can look at the differences in terms of their outcome as a measure of how much of a difference that treatment had in terms of their outcome. Now, the problem there is that when we're in environmental scenarios, we don't usually have the ability to apply both a treatment and a control. Really, only one of these is ever observed. And therefore, essentially, whatever we don't observe is really a missing data point. And if we're in a Bayesian framework, then it's very easy, or comparatively easy, to deal with missing data. We just treat this as a data augmentation type approach, and then are able to impute the missing values. So the way that we approach this, as I say, is the potential outcomes framework. We denote our outcome of the experiment Y for experimental unit I, either to be based on a control treatment, which we denote YI0, or based on an active treatment, which we denote YI1. And therefore, we have this mechanism of the potential outcomes where we observe only one of those. We either observe the control treatment or we observe the active treatment when WI is either 0 or 1 respectively. And then the missing observation is just whichever one we didn't apply. So 1 minus WI for the missing data. And then the idea from that is that if we looked at the table of the data in each row or each experimental unit, we have our WI. So these are the allocations of the data or to either the control treatment where WI is 0 or the active treatment where WI is 1. And then in the data columns, we either observe the control treatment yi0 or we observe the active treatment yi1. And then the question marks just relate to the missing observation in each case. And we're assuming that we observe exactly one of those in every case. It would be possible to extend this to a case where we don't observe either, but evidently that adds more uncertainty into the framework. So often the outcome of interest is really detecting or estimating the overall treatment effects. So this is what's the impact of a particular treatment on the outcome, either for a particular individual, which we call the unit level causal effect, or as an average overall observational units. And that's usually called the average treatment effect, or ATE. So in order to be able to do this, we need a way of estimating the missing observations for whichever treatment we don't observe, 1 minus WI. And the Bayesian approach, essentially the idea is to impute those missing potential outcomes, those Y miss values, given the observed values Y obs and the treatment assignments WI. Now, in many cases, if we've randomized the control treatments and the active treatments correctly, then we can often ignore the allocation treatment. But if we can't, then we can also introduce a model which directly accounts for that allocation of experimental units to each of the two outputs. And then once we've got that joint model over the missing unobserved values, we can then essentially simulate what would have happened under the alternative treatment, and then use that as our estimate of the average treatment effect, or calculate the average treatment effect from those estimates. So the approach has really 4 steps, which we iterate through. We first of all draw the model parameters given the observed data. So we're assuming that the joint model over yi and y miss might have some covariates and maybe some slope parameters or some variance parameters associated with it. So we use our Bayesian inference, so potentially an MCMC approach or whatever your preferred method is. We then impute all the missing potential outcomes. So there are yi miss given the model parameters. We then calculate the estimand or the estimate of the average treatment effect between the observed values, which are fixed, and the imputed values, which will be dependent on the iteration of the MCMC. And then we repeat that steps many, many times to get an idea of the uncertainty in those estimates. So we start off with a joint model FYI0, YI1, which determines the joint model over both treatment types. And that is the same for whether we observe missing or for the observed and the missing values. So the approach then is to derive the missing values given the observed values. We then derive the posterior of the parameters given the observed values and the allocation mechanism. We then have the next step, which essentially is the missing values given the observed values. And then we can derive from that the posterior distribution for tau. So this is essentially within an MCMC framework, and we're directly able to account for uncertainty in both the parameters and in the missing values. This relies on the fact that essentially, if we've got some degree of information about the underlying values, so we've got perhaps some covariates which we've collected at the same time, and we might be interested in what the effective or how the effective covariates changes depending on which treatment allocation has been applied. Then we need to be careful about what the distribution of those variables is across treatment groups. So we don't want to introduce biases into our results by conditioning on covariates which are different between groups. So if one covariate only appeared at low values in the treatment group and only appeared at high values in the control group, then there's potentially going to be biases introduced into the framework just because we don't have a baseline comparison between the two groups for that variable. So one thing we need to do, first of all, is to use a propensity score matching approach. So the idea of this is we're trying to generate this random control trial, which has the properties of that RCT by removing outlying data. So hopefully we don't want to do this for too many observations, but it may be that we can't quite match up an observation in the control group with an equivalent observation in the active group, and therefore we need to remove some of the data initially. But we can look at summaries of those to determine whether or not that's had an impact on the overall data or not. So just a bit of an aside, we were particularly interested here in zero inflated models, particularly for continuous data. And there's really two ways of approaching that, namely the delta models. So these are a two-part mixture model where we have essentially a Bernoulli distribution for the zeros and ones, and then conditional on a non-zero value, we then have some distribution, appropriate probability distribution for the non-zero values. So in the case of continuous positive data, we might use something like a gamma or log normal, are the two common choices, but essentially any proper probability distribution can be used here. The alternative is the Tweedy models. So these are a single family of exponential dispersion models that have property for particular parameter values of a zero inflation, so a point mass at zero, and then a right skewed positive distribution. The advantage of these tends to be that, as I say, they're a single distribution, but sometimes the delta models have been preferred, both because of the computationally easier to fit, and they also have this direct separation between the zeros and positive values, which can be interested in if you're interested in what the zero generation mechanism is. But there's essentially a lot of arbitrary choice between these two, and a lot of not very much work has been done on looking what the exact differences are between these in terms of model fitting. So we did quite an extensive simulation study using both the Tweedy and the delta models, just to see what properties they have in terms of estimation. The Tweedy models, as I say, for p between 1 and 2 have the zero inflation property, and they're essentially then equivalent to a Poisson gamma compound distribution, which may be more directly applicable for estimation purposes, but essentially it can be less interpretable than the original form of the Tweedy distribution. As I said, the delta log normal models are a mixture distribution of a probability pi for being zero, and then and some sort of right skewed positive distribution like log normal. So we ran this simulation study with different mean structures, and then we compared a variety of metrics on different models to determine which ones were best on the simulation, whether there's certain properties that are preferable for one model over the other in certain circumstances. We started off at very simple intercept-only models and then worked through more complex structures with polynomial terms, interaction terms, factor variables, etc., to determine how well each of the models are able to return parameters simulated from those models. Generally, what we found is that on the whole, the Tweedy model was much better. In general, at returning parameters, the mean squared errors were much lower. Even with delta log normal data, if we look at AIC, then there were quite a few cases where even with data simulated from delta models, the Tweedy model was still preferred as the preferred model fit. And there were also occasionally some issues with convergence of the delta log normal models, particularly in cases where you had very high proportions of zeros or ones. There just wasn't enough information then to fit these models correctly. But often the parameter biases were much higher for the delta model in general, particularly in the more complex structures when we started getting onto the more complex models. When we fitted the model from the Tweedy data, then it consistently preferred, much more persistently preferred the Tweedy model according to AIC. And again, the estimates of the biases and mean squared errors were much, much lower in the Tweedy model. So it does appear that in the choice between the two, if both are available, then the Tweedy model is more consistent over all possible model structures than the delta log normal, which seems to be quite sensitive in some situations. And again, as you start getting more complicated models, there were some real issues with how the delta log normal model was fitting, particularly in terms of convergence. And there were certain cases where if P in the Tweedy model tends towards 1, then there are challenges in terms of estimating the likelihoods there. So there tends to be some issue with convergence in that case. But generally, other than that, the Tweedy models were much more consistent. So just going back to the causal inference framework, we start off assuming a delta Poisson model here, although the same theory holds for gamma models or delta log normal models as well. But essentially, we can work out quite easily what the distribution of the observed values are, or for the joint model across observed and not unobserved values. And again, because of the properties of the zero inflated Poisson model, then essentially the joint model is also a zero inflated Poisson model, with just the parameters dependent on which of the allocation or which of the treatment groups you're in. And the weights then just correspond directly to the allocation mechanism. And that comes from the fact that Poisson random variables are closed under addition. So therefore, the missing values, so we can just simulate directly from a zero inflated Poisson distribution. For the delta log normal in the Tweedy model, this doesn't work quite as well because of the lack of the closed form under addition. And therefore, we need a slightly more complex model, which now becomes a mixture of Tweedies or a mixture of delta log normal models in that case. Because of the sensitivities we found with the delta log normal models, we're focusing here specifically on the Tweedy model. But here, again, it's a mixture of Tweedy distributions with the weights corresponding to the allocation mechanism, and then the parameters of the Tweedy corresponding to some mean structure, which we can put covariates in, and then some variance parameters as well. So the motivating data for this was from the London Atmospheric Emissions Inventory. So this is very high resolution data from London on a variety of different air pollutants. We're focusing here particularly on NO2, but exactly the same framework would work for PM as well, or for other different variables. So we looked at the EU Air Quality Directive, and their recommendation is that anything exceeding 40 micrograms per meter cubed would be considered a pollution event. So we therefore treat our allocation mechanism as being the control group is when the observation was less than or equal to 40 micrograms, or we assume that we're active group greater than 40. And the idea is we want to determine whether or not there's any impact on health outcomes, depending on whether or not you're subjected to either high levels or low levels or lower levels of NO2. And we didn't have any freely available data on health outcomes. So what I did to start with is just simulated some outcomes based on the real NO2 data, but also incorporating some additional spatial and temporal covariates into the model, and then assumed that the parameters associated with those covariates were different under the different treatments. And then we see here the distribution of the data under the two models, again, simulating from a 2D model to see how well we can retrieve those parameters. So we can see that there seems to be a slightly higher prevalence in the treatment group here in green relative to the pink group. But the idea is we want to fit this Bayesian approach to see whether we can detect that difference. So I simulated some data. As I said, we have an intercept and 5 covariates here. The second covariate is the NO2 value, and then we also have some spatial covariates and temporal covariates as well in our GLM. And we're assuming those estimates or those slope parameters for the covariates are going to be different depending on whether we're in the control group or the treatment group. We run our MCMC algorithm here, and just to show that we retrieve very well the simulated parameter values, which are here in red. Of all of them, this beta 2 seems to be the most furthest away, but it's still incorporated in the credible interval. So we are able to, even with this extra uncertainty of the missing data, we're still able to estimate very well the associations between different covariates, and we have the advantage of seeing whether there's any difference between the control group and the treatment group as to how they respond to the same external conditions. I also then calculated the average treatment effect across this, across the survey. And here we do indeed detect a significant positive effect of the treatment, suggesting that in this case, although we're dealing with simulated data, there was indeed a positive impact of positive causal effect of an increase in the NO2 values on the health outcomes, which we assume would be related to the prevalence of some sort of health condition. So the idea at the moment is we're trying to get permission to access some data from the same spatial regions, and the idea is to apply this more extensively on that data to detect whether indeed there are effects of health of NO2 or other particle matters. So just to finalize in conclusion, given the choice between the Tweedy and delta log normal models, we do suggest that Tweedy seems to be less sensitive in general, and even if the data were generated from a delta log normal model, the Tweedy model still seems to be able to do quite well at returning the same parameter values. And in the case where the Tweedy model was the correct data generating distribution, it's consistently much, much better than delta log normal models. We tried fitting this causal model with the delta log normal models, but the problem with it is that when you simulate the treatment effects on the missing data, because of the sensitivity of that model to choice of parameters, you can end up with simulations very much in the right tail. So we get very, very large treatment effects just because of the uncertainty built into that, or the sensitivity in that model. And therefore, the approach doesn't work quite as well under the delta log normal framework approach, particularly when you've got high proportion of zeros. But our 3D approach does seem to work well. We were able to retrieve very good estimates from our simulation studies. And we can also detect differences in how the covariates affect outcomes depending on which treatment group you're in. So just to say thank you to the funders, the 2 research associates were funded by a reinvigorating research grant, and also some of the computations were conducted on a reinvigorating research grant, and also some funding by the Edinburgh Mathematical Society. So just to finish off with some references that I mentioned during the talk, and thanks very much for listening. I'm happy to take any questions you might have.
Thank you very much, Ben. Are there questions for Ben? I have actually one. I see that you consider a binary like a treatment exposure.
Yes.
It's possible also to move from like a binary treatment to, like, for example, continuous treatment or exposure?
Yes, absolutely. So there are methods for dealing with alternative types of allocation. It becomes slightly more complex that you need to build in the allocation model in a more formal way. The advantage of the binary approach, providing you can assume that it's been relatively well randomized, you can really just ignore the allocation model in that case. So it makes things computationally more simple, but there's no reason why you're restricted to that. No, you can definitely use a similar approach with continuous treatments. Yeah, absolutely.
Thank you. Other questions for Ben? Okay, so thank you again.
Thank you.
And